This will be the main contents. So first we'll be discussing briefly about why stochastic optimization is needed, or how stochasticity comes into the optimization problem. And here I would like to focus a bit on the machine learning applications. Then I will be explaining about the improvements which we can bring to the gradient descent, which makes it more suitable for machine learning applications and stochastic problems. And finally, I'll be discussing about the ADAM, adaptive moment estimation algorithm. So let's start. So why stochastic? Possible reasons for stochasticity in the problem. One is the inherent function noise, and another is evaluation at random subsamples. This one comes when there is a machine learning application where you need to, for example, train from a set of data, and the set of data is too large. The batch kind of processing means like you are using the whole training set and finding the gradient of each of the points, and then using them to find the optimal model. In mini batch, what you do is you take a group of training data, find the gradient for that group, and then update the gradient in each step. So this is how the difference between batch and mini batch. Technically, the ideal stochastic GD optimization considers one point at a time, but mini batch is somewhere in between the true stochastic optimization and the batch gradient descent. And the mini batch or stochastic optimization is more suitable for online learning. That is, if you already have a model trained and you get a new data, you can always upgrade on the data to improve the model. And in stochastic optimization, we deal in machine learning training. Mostly the objective will be to minimize the expected function, and the function here will mostly be a loss function if you are doing a training sequence. So the prospective algorithm should average the gradients over the mini batches. So over each epoch, the gradient should be averaged to that is one of the key requirements for stochastic optimization. And we will be discussing about this particular section of stochastic optimization today. So we will be focusing mostly on stochastic objectives, and particularly the algorithms developed to cater for the high dimensional parameter spaces. This kind of problems mostly occur in machine learning training problems. And let us start with discussing the problem with simple gradient descent. So this is a simple gradient descent algorithm. Imagine that you have just two variables, b and w, and theta is your variable vector. So if you do iterates like this, theta alpha t is reducing with time. So there are two problems which occur here. The first one, just give me a second. Okay. The first one which you notice is like, suppose if you start at a point here, and then the iterates may go like this, like there will be too much oscillation in the direction you don't want, and it may not be much efficient. That is first problem. The second problem is if the problem reaches an area where the gradient is almost zero, then it will be stuck there. So these two are the problems of normal gradient descent. So to solve them, we have to use an adaptive learning rates. By adaptive learning rate, what we mean is we have to use a different learning rate in the X and Y direction. That is, the learning rate for B should be less and the learning rate for W should be high in this particular case. And one more thing which is necessary for stochastic gradient descent is the prospective algorithm should average the gradient over many batches. So that is one of the requirements for the stochastic gradient descent. And the general pattern of such an algorithm is like this. You have an upgrade. Instead of using a simple gradient, you use a function of moments or higher moments over the past time. So let us discuss about some of the example problems. First one is gradient descent with momentum, and then AdaGrad, RMSProp, and ADAM, and there are many more algorithms. So why there is no one simple or universal solution? This is because the problem differs. In sometimes you need to solve a sparse problem where most of the time the gradient is zero. Sometimes it will be dense, and the other requirements also matters. So based on the requirement, you may have to try any of these algorithms or a combination of them. Hence, there are a lot of algorithms you can find for stochastic gradient descent. So let us start with the first solution, gradient descent with momentum. Here the motivation is to average out the gradient to reduce the oscillation and deal with flat regions. So this does exactly what it mentions. First one is to calculate the first moment. So this one takes uh, averages out the moment mt, and this is the formulation of the algorithm. So you can notice that beta is 0.9 ideally, like it's one of the values possible. And so at beta is equal to 0.9, it is equivalent to your averaging out like the last 10 values of the gradient with a decreasing weight. And then using that to upgrade your iterate. So this one, in a sense, averages out these oscillations which you found here. I mean, initially it was like this. Now it will average out, so it will be a bit more smoother. You will expect something like this. So it will be a bit more smoother. And in case it reaches a zero gradient region, it will use the previous gradients and have a momentum to move in that direction. So in that way, it solves both those problems. Again, to improve the functionality of the algorithm, that is to create an adaptive weight for the different directions. We go for AdaGrad, that is adaptively scaling the grading agent. So here the principle is like this. First, you will find element-wise squaring of the gradient. You will sum it over the time 0 to t minus 1. And here, then you use it to scale your gradient vector. So here what happens is, like, suppose if the gradients were large in the past, then the scaling factor will also be large for that particular element, and hence the effective step size will be less. So in this particular case we observed, so suppose if this was the case, in the y direction, this you can notice that the gradient was large. So what AdaGrad does is it will reduce the gradient in the y direction because the sum of the past values will be high, and just again getting this same property, similar property. One of the problem with AdaGrad is, like, you can notice that the VT is being summed from 0 to t minus 1. So if your algorithm won't converge in like fast enough, the VT will be a very, very high value, and it may require high memory and high computation, etc. So to solve this, people have come up with RMSProp, and this was indeed proposed in an video lecture given in Coursera. So the algorithm works like this. Again, similar to the momentum method, it takes an weighted average of the square of the gradients. I mean, the second moment of the gradients. And this will, in effect, keep the VT from, like, increasing beyond a limit. And this one also works similar to AdaGrad. So this is the algorithm which they usually use. And for the RMS, the advantages and disadvantages of different algorithms, let us talk about them now. So first, the gradient descent with momentum. It is very simple. It is suitable for online algorithm. By online algorithm, what we mean is, like, if you have a new data, then you can easily use it to compute the new model without doing the whole algorithm once again. And AdaGrad, it works with well with sparse gradients. So suppose if you have some of the gradients zero for a long, long time, and then that gradient goes to like it gets a value in between, then the AdaGrad will give more weightage to that newly changed value parameter. And it is popular for linear and less complex models because it should converge faster. Otherwise, the value of that VT will go much higher. And coming back, then for the RMSProp, it works fine for online non-stationary settings. And again, RMSProp is having similar properties to AdaGrad as well. So now let us come to Adam. Adam is indeed a combination of uh, two of these algorithms. We can see it as a combination of gradient descent with momentum and RMSProp, comparing the combining the properties of both these. So what it actually does, you have to first define a step size, then beta 1 and beta 2 are its parameter, the other parameters, exponential decay rates for the moment, and f theta is your objective problem, and theta 0 is initial parameters. First, you set the moments to 0, and at time equal to t0, do the following iterations. So the first step here is to find the gradient, and then to find the first moment and update it like you do in the normal moment gradient descent with moment, and then you do update the VT factor. This using the second moment. This is done like your RMS algorithm, and then you compute a bias corrected first moment estimate. So I'll come to this why this is needed soon, and then you update the parameters similar to the way you did in your RMSProp. But the difference here is instead of the gradient in RMSProp, you are using the bias corrected moment here. And this algorithm is very famous because it combines both the advantages of RMSProp and the moment algorithm. And it is used for many machine learning applications as well. And first it is initialize the moment to 0. The bias correction is done to avoid bias towards 0. So you can see that the moments M0 and V0 are initialized to 0. So initially it may take a while to move from 0. I mean, it will spend more time around the 0. So to avoid this bias towards 0, we do the bias correction. So notice that beta 1 is scaled to a factor of t. So initially the denominator here is having an effect, and as t increases, the beta, this factor goes to the denominator of the bias correction goes to 1, and you will indeed use MT and VT as such effectively as time passes. So the epsilon here is used to avoid divide by 0. In case you have corrected VT is 0, you have to avoid divide by 0, hence epsilon is used. And moving to the next part, the recommended parameters for this algorithm. So they have recommended beta 1 is equal to 0.9 in the paper itself, and beta 2 is equal to 0.99, and epsilon is equal to 10 raised to minus 8, and the parameter step size needs tuning. So the main advantage here is like you can use beta 1, beta 2, and epsilon as in paper in most of your problems, and I have seen this in a couple of other literature as well. So they were guaranteeing like this configuration will mostly give you better results. And also you should note that there is an update rule. So the step size in Adam has upper bounds. So this is the effective step size of the Adam. And in the first case, you limit the step size to this alpha into 1 minus beta 1 by square root of 1 minus beta 2 if 1 minus beta 1 is greater than 1 square root of 1 minus beta 2. It is set to alpha otherwise. And proceeding, and this is mostly what I wanted to present. So if you have any questions, let us discuss.